Hello everyone, my name is João Carvalho and I will present the paper Ceramic AM Gantry Structures, Discretization and Connections between Beams and Columns. As we all know, additive manufacturing allows economy of means, more sustainable construction, mass customization, as well optimize design and function. A World Economic Forum survey from 2016 related to the future of construction states that the contour crafting of buildings is unlikely to happen. By opposition, the probability of the production of components by AM and advanced building materials is considered moderate. Finally, the production of prefabricated components is considered extremely high. This last point may justify why many research teams are now working in this field using AM technologies following a line of thinking based on discrete elements, where there's no need for the machinery to be bigger than the actual build. These are some of the projects that serve as base to this study and that clearly demonstrate the potential of this production process. However, these are isolated studies that consider both beams and columns independently without the complementarity that exists in a real context. Considering that and all the improvements, we think there is still a lack of research on a fundamental aspect of construction, which is the connections between components, namely when they have a structural role. In this sense, this investigation proposes the development of a set of gantry structures with load-bearing capacity composed by hybrid beams and columns. The material that we use is a fine stoneware without chamois with 35% of water content. The main problem of this material is related to shrinkage and deformations after firing. The fabrication used a typical liquid deposition modeling process where the extrusion of ceramic paste is controlled by a rotating spindle that regulates the material outflow. And as we can see here, the dimensions of both printer and oven are very strict, allowing only the production of medium-sized components. Considering all these restraints, namely printing volume, firing volume, behavior of ceramic material, and the results from the Future of Construction survey, we point to the study of discretization and connections between components as the main and final obstacle to produce fully functional systems. In order to solve that, we place on table a set of materials that could help us getting a constructible system. The materials were timber, rubber, mortar, glue, and concrete. These materials work between each component and serve mainly to avoid different ceramic pieces to touch, preventing cracks and explosions. Each of these materials were submitted to compression tests to evaluate which one is the best suited to work with ceramic. For the tests, we made 3 specimens for each material, with 2 and 3 stacked ceramic pieces, and we compare with specimens without separation material and with similar sized concrete specimens. After that, we pass to the development of columns that explore additional performative capacities that goes from structural reinforcement to thermal insulation, infrastructures, and ventilation. Here we have the steps corresponding to each of those functions, and here an example of the use of the structural reinforcement stave in order to build a column. Here the ceramic pieces serve not only as a reinforcement element but also as a formwork for the concrete. Contrary to the columns that study additional functions, the beams we develop focus on the definition of shell, internal structure, and the use of post-tension elements. To study shell and internal structure, we develop 3 types of specimens. The type 1 is defined by straight walls and an internal canal for the passage of steel cables. The second type is defined by a triply wave contour wall, and the third one uses a single wavy wall on the exterior and a triply periodic minimal surface as infill. For each of these structural drawings, the compression tests were made in 2 directions, simulating the force exerted by the post-tensioning, so horizontally, and by the applied loads vertically. Type 1 achieves the best results on these tests. We also simulate the use of Type 1 internal structure to assemble a post-tension beam with 2.7 meters span, as we can see here. The tensioning system consists of 3 steel bars tensioned with 16 Newton meters of torque. For the connections between beams and columns, we developed 4 types, all using steel cables or steel bars for tensioning. The first is a loose support, where each element is independent and there's no rotation blocking. The second type uses a metallic piece to join the elements, blocking the connection in all directions. Type 3 consists in a multi-link metallic connection, also blocking all directions. And finally, Type 4 is a wood interconnection with all rotation movements blocked. Although all systems have been designed, none of them have been yet tested, being this the next phase of this study. As results, we present the data obtained during the compression tests. This picture shows the remains of some specimens after tested. Here we can observe the comparison between 1, 2 and 3 pieces of stacked ceramic components without any separation material. The values show an exponential decrease on capacity as stacked elements are added. Now the comparison between specimens with the same number of stacked pieces, 2 in this case, or equivalent eyes for the concrete ones. The materials that present values superior to those without separation material are wood and the concrete infill, highlighted in green. The remaining material present much lower values than the reference specimen, as we can see here in red. Here we have the comparison between elements with 3 stacked pieces and equivalent eyes. As we can see, wood and concrete infill are again the ones that obtain the best results. Mortar and glue also present higher values than the reference, but not distant enough to be considered as an option. Despite being the best material to use with ceramic, would also have a downside. If we look to the standard deviation, we notice that the value is quite high. Since it's a natural material without any human processing, it is difficult to obtain an uniform material and uniform results. And with this, I finish my presentation. Thank you.